Morning, everyone. So today we're going to start into our last small section in our course. This one here will be looking at electrical circuits. We will primarily be looking at direct current circuits, so DC circuits. We'll make a sort of shout out to what is an AC circuit as well. But what's demonstrated for you here in the simulation here is a standard battery resistor circuit. I'll post a link to the simulation under the resources as well. We'll talk about how to draw these with circuit diagrams today, and I introduce some of the key terms that we're going to use in this section. So what we have here is a standard battery. This one here might be like a AA battery, AAA battery here. These ones here are designed. The terminal that actually extends out, this is usually the positive end. The other end here is going to be the negative end. Realistically, what's happening here is there's chemical reactions that occur inside the battery. There's anode and cathode. That was supposed to actually give you some true amount of voltage. But what we're going to see is as electrons are trying to diffuse and spread out and move through this battery, some of the voltage actually does already get lost. So what we're going to contrast is we're going to contrast what's called the EMF of the battery, the total voltage, the total amount of push that I was able to get from the battery, and by the time it actually runs through the resistance, we call that an internal resistance because that's going to be inside the battery itself. We're going to find that the net voltage is actually a little bit less. So we still have positive, we still have negative here. So far here, this is a current meter. It's actually measuring basically the flow of charge. So as these electrons here start moving around, they just animate it almost like with a wind turbine here. Depending on how quickly these charges are moving, that's actually going to give me a certain number of amps, and amperes is going to be a measure of the current, the speed with which the charges, and how many charges can actually pass by. So what's happening in this circuit here is we have three primary components. We have some voltage source. We have the electrons steadily going. Electrons have a negative charge. They always go from the negative terminal to the positive terminal. Unfortunately, when the laws of this physics was developing, we actually thought it was actually positively charged particles that were moving. They actually thought it was actually positive charges that actually went positive to negative. Unfortunately, we defined all our formulas based off of positive charges moving, in this case here, in the clockwise direction. Instead of redefining and fixing up all our formula sheets, we just said, oh, let's just call it conventional current. Let's just call it, it's the charge that we thought it was. Well, in reality, electrons are actually going in the opposite direction. We have basically wiring here. Wires are made out of nice conductive metals here. They carry charges really, really quickly. Charges can pass through pretty easily here. And what we have is we have a resistor that's marked off in this block here. And essentially the resistor is a solid. The resistor here, as the name suggests, it allows for some stoppage. It allows for some resistance, some holdback for the current. The electrons are trying to go through, but they're having a hard time running through this circuit component here. Realistically, even wires themselves have a resistance, although we're just going to assume that there's basically zero resistance in the wire, but it's just total resistance in the resistor component itself. Whatever device that you're running, we're going to call it the load. It could be a light bulb, it could be an MP3 player. That's going to eventually, because it's able to actually slow down the electrons, we can then taper some of that electrical energy off. So what's actually happening here is we're using chemical energy, we're converting it to electrical, we're letting these electrons here start flowing. As the electrons actually start flowing, because they start slowing down through the resistor, they trade in some of that kinetic energy, some of that electrical energy back into whatever you're trying to run it for. We're trying to run light, so light energy, we're trying to run buzzer, sound energy. It's trying to convert it back into energy form that we want. And they're just demonstrating that resistance as running through the different cores. We can show the voltage calculation. So voltage is always a relative comparison. So what's happening here is the electrons, by the time they make it to the end, let's assume that they have 0 volts. As they travel through the battery supplies them 2.88 volts. Voltage is actually a measure of how much energy is given per charge. They now, at this point here, has 2.88. As long as they don't get slowed down, they still keep the 2.88 because this is the only circuit component that they actually run through. They actually lose the entire 2.88 traveling through, so that by the time we have a rule that around any loop, the voltage should always cancel out. So that when there's a voltage calculation, we'll get into Ohm's law a little bit towards the end of this lesson. We can actually show the inside of the battery as well. We know electrons have a negative charge. Once they make it to the positive terminal, they actually have no desire to actually go to the opposite side. But when we say the battery actually supplies some free energy, some useful energy, it's like having these little fairies drag the electrons that arrive here and actually drag them to the opposite side here. By the time you actually drag up to the opposite side here, you're just going to flow through the current. You get pushed by the person behind you, and you travel down this path. So far, this is called the series circuit because there is only one path to go. Any electrons that travel out of the battery have to travel through the resistor itself. We can use the analogy of a slide here. Imagine these are the steps to get up to the top of the slide. By the time they're at the top of the slide, the electrons have only one way to go. They're going to fall down the slide before they get back down and ready to get up again. Even though current will be defined as the flow, it's going to be defined as how many coulombs of charge pass by in a given time. We're going to link it to an analogy. Current is sort of like the speed at which they actually leave. The higher the current, the faster they can actually travel through. So that's the inside of the battery here. What do you think is going to happen? In this case here, I can toggle the resistance. What's going to happen to the speed of these electrons, or this current meter here, as I increase the resistance? In this case here, I'm given the same voltage, 2.88 volts. That's a terminal voltage across the battery. As I increase the resistance, I make it harder for the electrons to actually travel. I want you to note the speeds of these electrons here. As you actually increase those ones there, you cause the cores of the resistance here to actually get a little bit bigger. In that case there, you could actually see the electrons are a little bit slower. I'm going to just dramatize that a little bit more. Let's make the resistance even higher. And you notice electrons really have a hard time traveling through there. It's a little bit hard to see on the scale here, but if you've been keeping watch here, the current here is actually slowing down. In some sense, electrons are really smart. They can, while they're sitting in the battery, they can see how difficult of a path is out in front of them. If they realize, oh, the resistance out here is actually really hard, not only do they know they're going to have to slow down through there, there's actually going to be less current that comes out from the battery. There's less people that are willing to take the path because it's a much harder pathway. If I instead swap out that resistor for something with lower resistance, I make it easier to travel through here, there may be not as much vibration here, then we're going to see not only do more charges actually are willing to actually make it out, the speed at which they actually go through the resistor is actually a little bit higher as well. So we see here the amperes, the current here is actually increased. The amperes are currently rotating in the clockwise direction. If I flip this battery around, we still have negative to positive, so the current can go the negative. The negative just means opposite the direction it was earlier. So in this case, it was 2.88. This is positive, and the orientation is now positive and negative. Let's see if I can get some negative 2.88. So I can flip the battery backwards. So negative 2.88. I now have the positive end here and the negative end here. The ferries will take them to the top of the slide. The electrons just go in the opposite direction. And now I just pick up a sign negative. The negative really doesn't mean anything. It just means it's opposite the direction as it was to begin with. As we start doing a Ohm's law calculation here, we're going to see a link between voltage, the current of the battery, and the resistance itself. And in some sense here, you may have everyday experience of this. If you run a battery for longer, or if it's too high voltage, if there's a lot of resistance, sometimes the temperature itself changes as well. What if my resistance stays fairly low and I slowly, gradually increase the voltage of the battery? I give these guys here a little bit more of a push here. They can actually start traveling a little bit faster. Now, if I'm using up all that voltage here in the resistor, you see that the resistor is actually changing in color. They're actually marking that this resistor is actually getting hotter. We always want to make sure when we set up a circuit to always have a resistor component, because we always want something to slow down the current, so that we don't end up short-circuiting, so that we don't end up causing a safety hazard of overheating. I don't know if this is animated for us here. If I keep upping the voltage here, right, that thing is getting really, really hot here. This one here would then be a danger risk of even catching fire. Right? So I'll post the simulation so you can play around with a little bit here. As you start doing Ohm's law, V is equal to IR. It's a pretty easy formula. We're going to see that. But what we're going to find is when we do Ohm's law, you actually need to do Ohm's law to each circuit component by itself. I can do a V equals IR just for this battery. I can do a V equals IR just for this resistor. Or if in this lesson we have multiple resistors, we can actually use Ohm's law in multiple different parts. So let's just flip back to our notes now. Okay, so let's just rehash some of those concepts that we just saw in that simulation there. This is going to be the start of our electrical circuits. We are primarily, as I mentioned, we're going to be looking at a DC circuit. The DC actually stands for direct current. Direct current essentially means the current only flows in one direction. It's a one way for the charges to go. The other type of current here is called AC current. AC current here is called alternating current. We actually get alternating current every time we plug a socket into the wall socket here. We actually get alternating current. I know it's not super clear. How come we have alternating current? Why don't we just make everything direct current? Next year when you actually talk about magnetic fields here, you actually realize we can generate electrical circuits by alternating magnetic fields, and by moving a magnet here, by oscillating it back and forth, we actually generate a voltage that's actually sometimes positive and then flips to negative, then it's positive, and it's just in the way we actually create the electricity that ends up being alternating. Now, a lot of our electrical devices only run with direct current. We have different devices called rectifiers, diodes, things like that, that can convert alternating current to direct current. But for our purposes for this year, we are mainly just looking at DC circuits, one-way circuits, not so much the alternating current here. This one here constantly flips direction. And actually for us in Canada, the frequency, nice link to our waves unit here, the frequency at which it flips is 60 hertz. So if you imagine here your wall sockets, there's a little elf inside your socket, and basically its job is to flip a battery back and forth 60 times every second. It's just alternating back and forth. The alternating current here would look something like this. So here's the voltage and here's the time. Alternating current, let's say it's a square wave, it gives me positive voltage. The elf here flips it, so now it's negative voltage, then positive, then negative. Right? That's what's actually coming out of the wall sockets. By running it through a device called a rectifier or a diode, it only lets current go through one direction. So let's say I hook up a diode, I hook up a one-way gate, and basically what's going to happen here is I'm going to then have the voltage and the time. Let's say the one-way gate only lets in the positive voltages. I'm only going to suddenly get only the tops of these waves here. I'm going to get a no wave going into the bottom. And in this case here, I don't want my devices to run sort of, now it has voltage, now it doesn't, now it has voltage, now it doesn't. What we're going to do is we're going to have little capacitors, different circuit components here to make this voltage, maybe store a little bit of this voltage and not let it drop off as quickly to try to mimic a rough direct current. In fact, all batteries that we have here are going to be direct current. We're going to see electrons only flow in one direction. All right? So we're going to mainly be looking at DC circuits. What I want to introduce to you here is what's called a circuit diagram. There's different symbols on this one here. Circuit diagram. You may have seen this a little bit in your junior science classes. For a circuit diagram, typically they say a circuit is comprised of 4 components. One is you have to have some electrical source. The electrical source here is typically going to be your battery. The battery here, as I mentioned, converts chemical energy. So chemical energy. And it converts that form into more useful electrical energy. Right. For a battery here, to show you that's an electrochemical cell, in Chemistry 12 we're going to actually talk more about the anode and cathode and what are the chemicals actually doing. For us, we're just going to say, well, inside the battery, we have an electrochemical cell. An electrochemical cell is just a fancy word for battery. Basically, we have a cell, we have a container, which basically, based on the reactions, it either gives me a positive voltage on one side or negative voltage on the other side. That's where your anode and cathode actually is. Based on your notation, the longer line is always the positive end, the shorter line is always the negative end. That's just one cell. That's actually going to give you the true amount of voltage. For a battery, typically our circuit component is actually many electrochemical cells, one after the other. Doesn't matter how many long legs that you do here. The short side will always be negative. The positive side will always be positive. So what's happening here is battery is actually many. So let's say here, so a battery is actually going to be many cells stacked up one to the other. They're all in the same orientation, so they all end up helping each other. This is sort of the workings of a series circuit. Like I mentioned, just for completeness sake here, let's pretend we had that AA battery again. There is an electrochemical cell here. The electrochemical cell is the true amount of voltage that the reactions are supposed to give you. So what we're going to say here is the EMF, okay, this is called the electromotive force. You get a lot into this next year. Electromotive force here, the electromotive force is the true voltage reactions are supposed to give you. So it's the chemical reactions, it's how the electrons get transferred that actually generate voltage. The EMF is the total voltage that you're supposed to get. However, because the battery has to be made out of physical components, there's material for the charges to actually pass through. As the electrons actually travel through here, we actually usually just show this all at once here. We call this an internal resistor. There's an internal resistance. there's always some blockage for those fairies here are trying to drag you to the top of the slide here. They're going to constantly slow you down there. That internal resistance will actually remove some of your voltage from you. Internal resistance, okay, due to diffusing through the battery, diffusing through the material, diffusing through the matter. So we're going to see in a second here, Ohm's law, we're going to see voltage is linked to current times resistance. So if EMF was supposed to be the total voltage I was supposed to get, my terminal voltage, by the time you actually see the voltage, by the time you put up this side here is the negative end and this side here is the positive end, you have this meter to sense how much voltage you're getting. The terminal voltage should have been the true EMF, should have been the total voltage that your reactions gave you, but we had to minus off the amount of resistance, the amount of voltage lost because of that internal resistance. So that's just nice info for you here. The VT here is called the terminal voltage. This is when we actually hook up our leads to the different sides, the different terminals, the positive and the negative. This is the actual voltage you have left over. It's a little bit less than the true EMF, than the total voltage your battery could have given you. We're always just going to use terminal voltage, so don't worry about EMF, but that's where we go from there. That's the first component. Second component here is we need to have some sort of conductor. In this case here, the conductor has to be able to carry current well. We know between metals and non-metals, metals tend to pass charges well. So conductor here, this is typically going to be our wires. This is going to be the pathway. This is going to be the circuit that the electrons are going to end up flowing through. Wires have relatively low resistance. What we're going to want to do is we want to put in our device that actually has some resistance. So this one here is going to be called your load. The load is a very fancy term for this is your resistor, and this really is your device, right? We're not wanting the electrons just to go just around the circle, just haphazardly here. We want to eventually convert that electrical energy here. So resistor actually is going to convert your electricity, all the energy and all the joules that they pick up from the battery itself. We're converting the electricity into whatever energy. Light energy here for a light bulb, converting it into sound energy for a buzzer. It's to actually run the device that you're actually trying to do it. Now, in some sense, you'll look at that and you'll say, well, those are the only three components I need. I need something that's the source. I need something that's going to push the electrons around. I need a pathway to actually go around. Because charges are unstable, the only reason why charges will travel from one place to the other is if they form a complete circuit. If they don't form a complete circuit, you're going to risk having buildup of charge. One side's going to become overly positive, overly negative. That's a really unstable, unfavorable state. The load is going to soak up that's the device that we're trying to run. It's going to use that electrical energy. Fine, that's all we need. Now it's more just sort of an environmental feature here. Sure, we just need those three circuit components. I'll draw a circuit diagram in a second here. But we don't want this thing constantly to be running. Let's say you're running a light bulb. There will be times that you'll actually want to switch the light bulb off. So just for just sort of an energy conservation perspective here, a fourth component here is usually going to be a switch. Switches come in many different shapes and sizes, things like that. But effectively, the switch will be your sort of your on-off. You can toggle it on. You can complete the circuit. You can switch the circuit off here. If the switch is in the on position, we say that the switch is in the closed position. The closed position means the circuit is complete. So complete circuit. There's no break. Complete circuit. If, however, we want to just, I'm done using the light here, I'm going to switch the switch to a open position. The open position we're going to see artificially breaks the circuit. And because it breaks the circuit, there is no complete pathway to get from one end to the other end. In that case there, the charges won't end up traveling. So let's see if we can draw these four circuit components here. It doesn't really matter where you do it because it's going to be a circle anyways. So I'm going to have a battery that's going to be some number of long lines, short lines. I know the long line is positive, the short line is negative. This one here is like my battery. I'm just going to sketch in the AA battery because we're familiar with it. But really it's just going to be that circuit component here. Realistically, your wiring may be coiled and twisted like that. That's actually going to become really hard to read. So for a circuit diagram, we keep everything 90 degrees if we can. I'm going to keep the road here going straight up out of the battery, going to the side, downwards, and then back down the other side here. So that's my typical battery here. So far, I have my source, I have my battery. This is going to provide me the oomph, provide me the push to get out of the battery itself. The conductor here is going to be in red here. The conductor is just the wiring. It's going to complete the circuit for me. never do this right now because I actually don't have any resistor. In this case here, the electrons will flow so quickly through it, the battery, again, just like you saw in the simulation, is going to end up overheating. What we're going to do is we're going to put in the load. Now, it doesn't matter if you put the load down here or the load over here, right? If it's one complete circuit and if the flow of charges has to pass through it, it doesn't matter where it passes through. This guy here is going to be your load. This guy here is going to be the device that we're actually trying to run. So there again, we have our three main circuit components. Great. We're able to convert, in this case here, it was chemical energy over to electrical energy. Our load is converting electrical energy to whatever form that I want. Sure, every time there's a transformation, I'm always fighting this losing battle, right? First law of thermodynamics, I can't create energy out of nothing. And the second law of thermodynamics, with entropy increasing, I'm always having less and less. Some of this heat here is gradually being lost in the environment. So if I were a power plant designer here, I'd like to be able to convert the energy with as little transformations as we get, because I know each time I convert that form of energy, I end up losing a lot along the way. So we have this battery, we have the load here. Again, for the switch here, it doesn't matter where you put it. The typical sort of the symbol for a switch here is you just draw two dots like that. It sort of looks like a doorway. If the doorway is in the closed position, you notice that it completes the circuit. This one here is going to be on. I can have a switch. I can draw another switch here. I can have two switches. So this switch here, if I open the switch, this switch here is now in the open position. It's like an open door. The open position here would have broken up. It's like this wiring here is no longer connected anymore. When there's no circuit, when there's no one pathway to get from start to finish, the electrons won't actually go. So those are your four main circuit components. Try to make everything as 90 degrees as you can. If you have later on for parallel circuits and wires cross over other wires, you just do that little loop symbol here, and that way it'll show you your way around. Now, one other thing here is when we start talking about electron flow here, unfortunately, like I mentioned, historically we thought it was actually positive charge carriers. We called them positrons. They're not actually protons. They're actually the antiparticle of an electron. We thought there were these E's that have positive charges. Well, if I'm positive, of course, I want to run away from the positive charge. I'm actually going to want to flow in this direction here. I'm going to want to flow positive over to negative, right? They did that fine. They did a lot of derivations, a lot of formulas with positrons, no problem doing this. And later on, they're like, we actually, in reality, electrons actually have negative charges. Electrons are actually doing the opposite of them. Electrons having a negative charge actually themselves flow from negative to positive. Just like I mentioned, instead of reworking all your formulas and whatnot, they just gave it two different names. They called your conventional current. This is actually what we're going to be calling I. Conventional current I assumes positive charges. So these positrons, positive charges flow from the positive terminal to the negative terminal. Well, you're like, well, that's not true, right? It's not positive charges. Well, that's why we just give this a different name then. In reality, we have what's called electron flow instead. It's actually electrons that have negative charges that are actually the ones that are moving. Electron flow is actually going to be the opposite. We actually have negative electrons, negative flows from the negative terminal to the positive terminal. Right? So when we use Ohm's law, V is equal to IR, all that current here is always going to be conventional current. It's always going to sort of be a mistake. We thought it was positive charges going in one direction, but in reality it's actually negative going in the opposite direction. No real problem, however, because it's going to be one circuit anyways. Our formulas just are pretty easy in either direction. So let me just introduce to you in this lesson here our main formula. You're going to see this formula over and over again. This guy here is a guy called Ohm's law. Ohm's law, it's actually defined for resistance. Ohm's law at first is defined, if you want to find the resistance of something, it's going to be voltage divided by the current. So in this case here, resistance, this is how much stoppage there is to flow. Resistance is measured in ohms, right, in honor of Ohm. It's going to be a comparison between V, which stands for voltage. Voltage is sometimes also called the potential, but careful, potential is not potential energy. That's two different concepts, right? They couldn't have been more confusing. Potential is voltage and potential energy is not, huh? Okay, but voltage here by definition, this is the energy given per, we use coulombs to measure charge. That's just the unit of it, per coulomb of charge. So imagine, right, it's our battery that generates this voltage here. Our electrons here, as they travel through the battery itself, I'm actually doing conventional current here. So as I have positive charge carriers, as they try to travel through the battery itself, basically the battery gives each of these charges some energy. And for every coulomb worth of charge, right, as they travel through, how much energy I give it is actually this voltage. The more voltage I give it, the taller the slide is going to be. I give each coulomb of charge here more energy to work with, and they're actually going to be able to go out the battery here with a little bit more speed, with a little bit more current. So in this case here, current, technically here, again, this is conventional current. This is your I. Current here, it's actually a measure here. It's a measure of charge that passes per second. So if you want a formula for that, the current is equal to the Q divided by the time, where Q is charge. It's setting up like a station here, and it's actually measuring, well, how many charges are actually passing by as I look at my clock per second. We're going to use the analogy of how fast it goes. It's technically not a speed per se. It really is counting how many charges actually pass per second, but just for analogy's sake here, we're going to use speed. If you want the formula for the other one here, voltage can also be, well, it's the energy that's given per charge. Next year, you're going to do a whole bunch of other circuit components. You'll look at electric fields, you'll look at magnetic fields here. You'll deal with electrostatics and different formulas in more detail. For us, we're just mainly concerned with Ohm's law. I don't really like having this upside down relationship. I'm going to just rearrange it for V. So therefore, Ohm's law is usually written V is equal to IR. That formula there is simple as that. Okay, so let's rewrite it here. Voltage, we're going to use, it's going to be in some volts, 6 volts, 1.5 volts. I is the current. We're going to use amps for that, another SI unit. Amperes is the full name for that. And the R is the resistance, how much stoppage to flow. Impedance is actually something else. That also sounds like a slowing down word. Resistance is measured in ohms. And in some sense here, when we deal with these charged things here, just like we saw with the relativity and half-life stuff here, the energy numbers happen to be really, really tiny. Sometimes an amp is a huge amount of current. So many times we're dealing with milliamperes. Resistance, we typically deal with maybe mega ohms, right? The order of magnitude might be different, but ultimately these are the SI units that we want. Just as we just want to practice through a question here, we'll do a lot more with this in tomorrow's lesson. Let's say I give you a battery. Let's say this is a 9-volt battery. Typical 9-volt battery here, sure, it would have the terminals on the both sides, right? So it's like positive and negative like that. It's a relative, but as it pertains to a circuit diagram here, we're just going to draw a pathway. We're going to pretend we have positively charged particles going from the positive terminal through some load and then back to the other side here. So we have a 9-volt battery. The battery is supplying the voltage. Obviously, our load is supplying the resistance. And then we have a current that's ending up flowing through the wiring itself. What I want to just introduce to you in this lesson, we'll practice this some more tomorrow, is basically when you use Ohm's law, sure, we can sort of see where the voltage comes from, current is, where the resistor is. What I want you to focus on, however, is you can actually do Ohm's law just for this battery. You can do Ohm's law just for this resistor. It's not just, oh, let's just find the V, let's just find the I, and let's divide them. We're done. Okay, we can actually use Ohm's law in different circuit components. So let me just make that note here. It's going to become important later on. Ohm's law applies to each component separately. So sure, you might have to use this easy equation V is IR many times, but you need to do it for each resistor that you actually have. So let me just introduce you to the first type of circuit. This first type of circuit here is called a series circuit. A series circuit is a one-pathway circuit. Any cars that leave the parking lot, that is the battery, they have to travel around the loop. It has to be a complete circuit. If there's any break here, the charges won't move. If there is a complete loop here, they're going to travel through every single resistor they run into, and they're going to end up getting back the way it came. So I'm going to keep it fairly simple here. Let's start off again with our 9-volt battery. Let's say we have this time 2 resistors. One of them is a 2 ohm resistor, and we run into another resistor that's a 3 ohm resistor. Right? So we see that series. My conventional current, which goes from positive to negative, all of them have to flow through both of these resistors. Right? So when we think about doing Ohm's law here, I know 9 volts should be the total voltage that we have. That's the total amount. I need to not use up all 9 for the first resistor because there's another resistor I need to travel through. In fact, this resistance is higher. I would expect there's even more voltage. So that 9 volt has to be divvied up between these two resistors here. I mentioned chargers are somehow they're really smart. They can look out of their circuit. They can actually realize what's upcoming. Depending on how hard the circuit is coming out, not only do they slow down to compensate, they may not even risk coming out of the parking lot at that time. It's a little bit hard at this point here. If I'm trying to do Ohm's law, it does say I have V, I have a R. You'd imagine I can do a V because I R. But again, this problem here is this voltage, because it needs to be divvied up between the 2 and 3, I can't use Ohm's law just yet. Nor can I just go, oh, let's go V because I R here. Again, I don't know how much voltage nor the current. I need 2 out of the 3 to actually solve for what the voltage is. So I'm trying to use Ohm's law, but I'm trying to do Ohm's law for each part separately, and it's impossible to do. What we're going to do is we're actually going to try to do what's called an equivalent resistance. Try to swap out this combination as set up. We're going to run into 2 resistors no matter what you do. One sort of medium rough patch, one really rough patch. See if you can swap out this circuit for an equivalent resistor. So see if I can replace this 2 resistor combo. See if I can resist it with just 1 resistor so that my circuit becomes a little bit easier. So that my circuit looks like what I drew earlier. I had a 9 volt battery. I have some equivalent resistance. They can call it REQ or they can call it RT, total resistance like that. So that if you can tell me how much current is going through here, I know the equivalent resistance, I can figure out the current myself, and because these are equivalent, the current here is this current here, and I can backtrack and do my calculations again. So for this, we're actually going to get some formulas for when you do equivalent resistance for series, we'll do parallel for tomorrow. This one here is actually a fairly simple derivation. In series, so we know we're series here, we know the total resistance has to be divvied up between the 2 and the 3 here. So what's happening here, this is actually going to be, fancy name here is going to be called Kirchhoff's loop rule. And it basically says the sum of the voltages, if you add up all the positives and the negative voltages, all the gains from the battery, losses from the resistor, sum of voltages around any loop is 0. So basically using the slide analogy, you might walk up to the top of the slide. By the time you're done the circuit, you have to have been back down to ground level, and now you're ready to go around again. So what's happening here is, let's start a loop. Let's start at any point in the circuit. Let's start here. Around this loop, by the time I get back here, I better have used up all 9 volts. So in this case here, I would have picked up 9 volts from the battery. I'm going to use up some of the voltage in the 2, some of the voltage in the 3, and now I'm back down to 0 volts. It may be a little bit clearer if I actually drew the dot down here. Sorry. So let's imagine I started down here. I can start at any point in the loop. As I go through the battery, I pick up 9 volts. As I go around, I'm going to use some of the voltage here, some of the voltage here. I minus some volts here, minus some volts here. By the time I get back, I want to make sure I'm back at ground level. I want to make sure I'm back at 9 volts. So in this case here, I can make a note. V total should equal to so I can actually write that down first. So V of my battery, normally you don't need to show all this work. V of the battery, I gain 9. I minus off the voltage through the 2 ohm resistor. I minus off the voltage through the 3 ohm resistor. This is supposed to give me 0 volts. The total voltage should cancel out. Or you can say the V of the battery is basically going to be divvied up between the 2 ohm resistor and the 3 ohm resistor. If we use Ohm's law for each of the circuit components themselves, we say V is equal to IR. This is the current and the resistance of the battery. This is going to be the current times the resistor with 2 ohms plus the current times the resistance with 3 ohms. In some sense, all I'm saying here is because we're in series, because any car that leaves my battery has to travel through the 2, there is no other pathway to sort of sidetrack and actually get back to the battery itself, the current is actually the same. So current, whatever charges flow through the first resistor will flow through the next resistor, will flow through the battery. The current goes through every component. So the I is actually the same in this case here. So if I factor out the I times the R of the battery is equal to, these i's here are the same, so I'm going to pull out the I. I'm going to have R of the 2 ohm resistor plus R of the 3 ohm resistor. The current is going to be the same. This current and that current are going to die away. So what this actually generalizes for me here is, because the current is actually identical, to find the equivalent resistance in a series circuit, the equivalent resistance, that's what the battery is applying. It's a little bit easier to think about just as a total. What combination can I replace my battery with? This is actually going to be R1 plus R2 plus any number of resistors that you have. So if you look back at this resistance here, it shouldn't be that surprising. Well, if I'm running through a 2 ohm resistor and a 3 ohm resistor, this is the formula that it is in series. My equivalent resistance would just be 2 plus 3. It'd be like running through a patch that's 5 ohms, because I have to run through both. There's no other way to turn around. Now if I run through 5 ohms, now it's a lot easier. If I do my loop rule again, I gain 9 going through here. There is only one resistor now. I know I now need to drop exactly 9 volts. If I just did Ohm's law just for this part, V is equal to IR, I'm going to lose the 9 volts. I'm not going to worry about positives and negatives, right? If I have negative voltage, it just means the opposite way. I need to this time truly lose 9 volts. It's not divvied up between the two anymore. 9 volts, what's the total current, the equivalent current, if my total resistance is 5? My current here I'm getting here is 1.8, and the unit is amperes. So the flow of the charges, how fast can I move around the circuit, is actually going to be 1.8 amperes. Now what's amazing about this here, I use Ohm's law for my equivalent resistor because it's equivalent. The current 1.8 amps here is actually going to be the 1.8 that actually came out of here, 1.8 amps. And now that I have more information, I know the current and I know the resistance, I know the current and I know the resistance of the other one, I can verify that I've used up all 9 volts. So let me just end off with that calculation here. Let me just redraw it on the side so it's a little bit clearer. So we had a 9 volt battery. I did my equivalent circuit. I realize it's 1.8 amps. I know I have a 9 volt battery. I know the cars that will risk it out of here is 1.8 amps. They are going to first run into a 2 ohm resistor, then run into a 3 ohm resistor in series, one after the other. Again, when I use Ohm's law, it's an easy formula. V is equal to IR, but I need to go V is IR for each component itself. Now I know I have 1.8 amperes worth of cars times the 2 ohm resistor. That gives me 3.6 volts. On the other one here, I can use Ohm's law, same formula, but applying to a different circuit component. The current is the same. The 1.8 cars that made it through the first resistor will still make it through the second resistor, but the second resistor actually has 3 ohms, and in that case, when I multiply it, I believe I get 5.4. Let's see if Kirchhoff's loop rule is actually applied in my real circuit. I had gained 9 going through the battery. I'm going to minus 3.6 because that's taken away, that's used up for my light bulb, minus off 5.4. And if you add up 3.6 and 5.4, no surprise there, this is actually giving you 9. So I pick up 9. Over the course of the 2 resistors, I lose my 9 volts so that I'm back down at the bottom of the slide. I'm ready to take the staircase up again. I gain the 9 volts. By the time I end, I use up 3.6 in my first resistor, I use up 5.4 in my next resistor, and now I'm back down to 0. Those fairies can then take me up again. This is for that first resistor, this is now for the second resistor. Right? So again, I just want to demonstrate to you, the rules are very simple. It's just Ohm's law, but you're going to have to apply Ohm's law to each component separately. Tomorrow we'll come back and we'll take another look at sort of parallel circuits and sort of combination style circuits, and we'll go from there. Thanks, guys.